Hello students, welcome to this video presentation on the new chapter called Waves. This chapter is given as chapter number 15 in Physics for class 11 of NCERT syllabus. In the previous chapter, we studied the motion of objects oscillating in isolation. Whereas in chapter number 15, we will study about a system which is the collection of a number of objects. A material medium provides such an example. Here, elastic forces bind the constituents to each other, and therefore the motion of one object affects that of the other. Classic examples are, if you drop a little pebble in the pond of still water, the water surface gets disturbed. This disturbance does not remain confined to one place but propagates outwards along a circle. If you continue dropping the pebbles in the pond, you will see circles rapidly moving outwards from the point where the water surface is disturbed. In this chapter, we will first introduce the topic, followed by transverse and longitudinal waves, displacement relation in a progressive way, the speed of a traveling wave, and the principle of superposition of waves. In part 2, we will discuss about the reflection of waves, the beats, and Doppler effect. We will also solve in the next part some question and answers. So I welcome you once again. Please note down the important points. Introduction. A wave is a disturbance which propagates energy and momentum from one place to the other without transport of matter. There are three types of waves: mechanical waves, electromagnetic waves, and matter waves. In this chapter, we will study about only mechanical waves. However, we will describe briefly all the three types of waves. The first one is mechanical waves. Waves such as waves on a string, water waves, sound waves, seismic waves are called mechanical waves. These waves require a medium for propagation. They cannot propagate through vacuum. Please note, mechanical waves cannot propagate through vacuum. They involve oscillations of the constituent particles and depend on the elastic properties of the medium. The next type of wave is electromagnetic waves. Electromagnetic waves are created as a result of vibrations between electric and magnetic field. We are going to study about electric and magnetic field in class 12. However, just note that the rays emitted by distant stars reach us through space, which is practically a vacuum. Electromagnetic waves do not necessarily require a medium. They can travel through vacuum. Light waves, radio waves, or X-rays are all electromagnetic waves. The third type is matter waves. These are associated with the constituents of matter like electrons, protons, neutrons, atoms, and molecules. They arise in quantum mechanical descriptions of nature. They are more abstract than mechanical and electromagnetic waves and have found applications in several devices basic to the modern technology like electron microscopes. We will study about matter waves in higher classes. Propagation of sound waves in air. In this chapter, we will study mechanical waves which require a material medium for their propagation. As the wave passes through air, it compresses or expands a small region of air. This causes a change in the density of that region, which includes a change in the pressure of that region. There is a restoring force proportional to the disturbance, just like a spring. Thus, the compression or rarefaction moves from one region to another, making the propagation of disturbance possible in air. In solids, a similar arguments can be made. In crystalline solids, atoms or group of atoms are arranged in periodic lattice. In these, each atom or group of atom is in equilibrium due to forces from the surrounding atoms. Displacing one atom while keeping the others fixed leads to the restoring forces, exactly as in the case of a spring. So we can think of atoms in a lattice as endpoint with springs between the pairs. Transverse and longitudinal waves. There are two types of waves in nature. They are transverse and longitudinal. We have seen that the motion of mechanical waves involves oscillations of constituents of the medium. In transverse waves, the particles of the medium execute simple harmonic motion about their mean position in a direction perpendicular to the direction of the propagation of the wave. Please see the figure on the right hand side on your screen. Here there are two directions. One is the direction of motion and the particles of the medium executing simple harmonic motion. So the particles in this figure are shown as execute simple harmonic motion in a direction perpendicular to the direction of the motion, wave motion, propagation of motion. The transverse waves travel in the form of crests and troughs. So crest and troughs. Now what is a crest? A crest is a portion of the medium which is raised temporarily. That is, the upper portion is a crest. And a trough is a position which is depressed temporarily. That is, the lower portion is the trough. Examples of transverse wave motion are movement of a string in a guitar, that is musical instrument, sitar or a guitar, and waves on the surface of the water. Transverse waves cannot be transmitted into liquids and gases. So note that transverse waves cannot travel through liquids and gases. Then next type is longitudinal wave. If the particles of the medium vibrate in the direction of wave of motion, the wave is called longitudinal. So the particles vibrate in a direction along with the direction of the motion. So please see here the direction, the waves, the particles vibrate along the direction of the wave motion. Here the waves travel in the form of compression and rarefaction. That is, you see here there is a compression region and there is a rarefaction region. So the wave travels in the form of compression and rarefaction. A compression region is the medium in which particles are compressed. A rarefaction is a region of the medium in which particles are rarefied. So rarefied means expanded. Examples of longitudinal waves are sound waves that travel through air in the form of longitudinal waves. Waves produced in a cylinder containing a liquid by moving piston back and forth. Ultrasonic waves in air produced by vibrating quartz crystal. So this is vibrating quartz crystal is produces an ultrasonic waves which are longitudinal in nature. These waves can be transmitted through solids, liquids and gases. So the waves which travel through solids, liquids and gases are longitudinal waves. In addition to the two types of waves, we have a combination of transverse and longitudinal waves, like motion of a kink in a longitudinal spring produced by displacing one end of the spring sideways. Waves produced by a motorboat sailing in water are the examples of combination of transverse and longitudinal waves. Displacement relation in a progressive wave. A progressive wave is the wave that moves from one point of the medium to another. For mathematical description of a traveling wave, we need a function of both position x and time t. Such a function at every instant should give the shape of the wave at that instant. Further, at every given location, it should describe the motion of the constituent of the medium at that location. If we wish to describe a sinusoidal wave, we have to plot the graph as shown in the screen, on the screen. So here the x is the direction of motion and y plot on the y side, it is the amplitude A. Hence, the displacement in a sinusoidal wave propagating in positive x direction is given by the relation y of x of t equals a sine of argument, that is kx minus omega t plus phi. Let it be equation 1. Here small a is the maximum displacement or amplitude as shown in the figure. The letter k in the argument is the angular wave number. It is also called the propagation constant. Omega is the angular frequency, and the items within the bracket, that is argument, are kx minus omega t plus phi. All the three terms combined together is the phase, and phi is the phase constant or phase angle. The next item, that is the physical quantity, is the wavelength. It is represented by Greek letter lambda. Wavelength is the distance traveled by the wave in one time period, and it is known as wavelength. Hence, it is the length of one wave, and it is shown in the figure. You see here, from the point x1 to another point, say x2, is the wavelength lambda, as plotted on the direction of x-axis or position. The distance between two consecutive crests or troughs is given by lambda, and its relationship with the angular wave number or propagation constant is lambda is equal to 2 pi divided by k. The next physical quantity is represented by symbol V, and it is called frequency. Hence, frequency is normally represented by nu. In some of the books, they have used the symbol letter small n, or it is also used sometimes small letter f. F or n or nu, all are same, and these are called frequency. Frequency is the number of vibrations completed in 1 second. Time period, capital T. Time period of vibration is defined as the time taken by the particle to complete one vibration about its mean position. Please see the figure here. In this second figure on the screen, x-axis is t, time t, and y-axis it is amplitude. So the graph sine wave is plotted as shown on the screen. The amplitude, the maximum displacement in the y direction is shown here, and in the horizontal distance, that is the distance between two troughs in the screen, is capital T. Capital T is called the period. Instead of troughs, you can even take the two crest. This is the one crest, and this capital T here is also equal to the distance between the two crests. The relation between frequency and time period, that is the relation between nu and capital T. So time period is given by time period is equal to 1 by frequency. That can also be written as capital T is equal to 1 over nu. relation between velocity v, frequency nu and wavelength lambda. So therefore v is equal to nu into lambda. The speed of a traveling wave. To determine the speed of a propagation of a traveling wave, we have to fix our attention on any particular point on the wave and see how the point moves in time. It is convenient to represent the motion of a wave, the crest or a trough, as shown in figure on the screen. The figure gives the shape of a wave at two different instants. Please remember that this is the figure, though shows two waves, but it is only the plot of one wave but at different instant. For example, this dot represents the wave at a time t. After a time delta t, it moves to the position second here, that is t plus delta t, which is shown as another curve for our convenience. This plot is in the direction of motion, that is x, and amplitude is in y-axis. The figure shows the shape of a wave at two instants of time, which differ by a small time delta t as said. The entire wave pattern is seen to shift to right, that is the positive x-axis, by a distance delta x as shown in the figure. The speed of the wave is given by the relation delta x by delta t. The wave will move with the same speed v. The motion of a fixed phase of a point on the wave, that is the point dotted on the crest, is given by the relation kx minus omega t is equal to constant. Here all the represent the standard symbols as described in the previous slide. Let it be equation 1. Thus, as the time t changes, the position x of the fixed point, that is a dotted point, must also change so that the phase remains constant. Thus, kx minus omega t of the equation 1 will become, after delta t, it travels a distance delta x, so x becomes x plus delta x. Therefore, the left hand side becomes k into x plus delta x minus of omega into t plus delta t, as t has changed from t to t plus delta t. Therefore, equating both left hand side and right hand side, we get, and substituting and cancelling the common terms, we get k into delta x minus omega into delta t equals 0. Thus, taking delta x and assuming delta t to be very small gives the relation delta x dx by dt equals omega by k. That is rearranging the previous equation. That is omega dx by dt is nothing but velocity v. Let it be equation 2. So relating omega to t, that is time period capital T, and k to lambda, we get v is equal to omega is 2 pi nu. It is nu, that is frequency, divided by 2 pi by lambda. That is equal to, the simplifying, lambda into nu equals lambda by t. That is nu is 1 over t. That is, so v is equal to lambda by t. Let it be equation 3. Hence, equation 3 is a general relation for all progressive waves, which shows that the time required for one full oscillation by any constituent of a medium, the wave pattern travels a distance equal to the wavelength of the wave. Second point, it should be noted that the speed of the mechanical wave is determined by the inertial, that is linear mass density for strings, mass density in general, and elastic properties, that is Young's modulus for linear media or shear modulus for bulk modulus of the medium. The medium determines the speed. Equation 3 also relates wavelength to frequency of the given speed. As remarked earlier, the medium can support both transverse and longitudinal waves, which will have different speeds in the same medium. We will further discuss about different mediums in subsequent sections. The speed of a transverse wave on a stretched spring. The speed of mechanical wave is directly related to the restoring force set up in the medium and inversely proportional to the inertial properties, that is mass density of the medium. So the two factors are restoring force and the linear mass density of the medium. For waves on a string, the restoring force is proportional to the tension T in the spring, and the inertial property in this case will be linear mass density, which is defined as mass per unit length of the string, and its dimensions are m into L to the power of minus 1. So using the dimensional analysis, we can write the speed v is equal to tension T divided by the mass density mu. Therefore, we can write the dimensions of V as ml t to the power of minus 2. That is the tension. The dimensions of tensions, which is a force, is ml into t to the power of minus 2. And the dimensions of mass density mu e are ml to the power of minus 1. Simplifying, we get L square t to the power of minus 2. Therefore, the speed v can be written as v is equal to c into square root of tension T divided by the mass density mu, where c is the undetermined constant and its value is found to be practically as 1, that is c is equal to 1. Therefore, we can write v as v is equal to speed is equal to square root of capital T tension divided by mass density mu. The speed depends only on the properties of the medium, that is tension and the mu. It does not depend on the wavelength and frequency of the wave. Please note, the speed does not depend on the wavelength or frequency in case of a stretched spring. Of these two parameters, lambda and nu, the source of disturbance determines the frequency of the wave generated. Given the speed of the wave, if v is known medium, then we can calculate the wavelength as wavelength lambda is equal to v by nu. Let us solve an example, a numerical example. A steel wire 0.72 meters long, the length of wire is 0.72 meters long, has a mass of 5 into 10 to the power of minus 3 kg. If the wire is under tension 60 N, what is the speed of the transverse waves on the wire? Please note down the given parameters and we will solve it. Answer: mass per unit length of the wire is given by, that is mu is equal to, we know mu is equal to mass over length. Mass is given as 5 into 10 to the power of minus 3 kg and length is 0.72 meters. So that is equal to, substituting the values and simplifying, we get the value of mu as 6.9 into 10 to the power of minus 3 kgs per meter. It is also given that the tension is 60 newtons. Therefore, we can calculate the speed of the wave on the wire as V is equal to square root of T by mu, that is equal to square root of 60 N by 6.9 into 10 to the power of minus 3 kg per meter. Simplifying and calculating the values, we get V as V is equal to 93 meters per second. Speed of a longitudinal wave, that is the speed of a sound wave. In longitudinal wave, the constituents of the medium oscillate forward and backward in the direction of propagation of wave. We have seen in the previous section that the sound waves travel in the form of compressions and rarefactions of small volume elements of air. The elastic property that determines the stress under compressional strain is the bulk modulus of the medium, defined by the relations B is equal to minus del P divided by del V by capital V. Here, the change in pressure delta P produces a volumetric strain delta V by V. B has the same dimensions as pressure and given in SI units in terms of pascals. The inertial property relevant for the propagation of wave is the mass density rho, whose dimensions are ml to the power of minus 3. The quantity B by rho has the dimensions ml to the power of minus 1 t to the power of minus 2 divided by ml to the power of minus 3. So the dimensions of rho are ml to the power of minus 3 and dimensions of B are ml to the power of minus 1 to the power of t to the power of minus 2. Simplifying this ratio, we get the value of B by rho as L square into t to the power of minus 2. Let it be equation 2. Thus, if B and rho are considered to be the only relevant physical quantities in the case of longitudinal wave, that is speed of sound, we can write the solution as V, the speed of sound wave, equals C into square root of B by rho. Let it be equation 3. Here V is the speed, C is a constant, undetermined constant from dimensional analysis. The exact derivation shows that the value of C is equal to 1. This derivation, exact derivation, is beyond the scope. Hence, we have used only the dimensional analysis as per NCERT syllabus. The value of C is 1. The general formula for the speed of longitudinal wave is given by V is equal to square root of B, that is the bulk modulus, divided by rho, that is the mass density. Let it be equation 4. The speed of longitudinal waves in linear medium, that is in the case of a solid bar where the lateral expansion is negligible, and we can consider the bar to be only under longitudinal strain. Hence, the speed of the longitudinal wave in the linear medium is V is equal to square root of Y by rho. Here, instead of bulk modulus, we are using the constant Y, which is the Young's modulus of the material. Please refer the chapter number 9. Go back and refer, and I am giving also the link, and refer the parameters for the bulk modulus and Young's modulus. Table shows on the screen shows the relationship between speed of sound in case of gases, liquids and solids. The analysis of this is very important. Liquids and solids generally have higher speed of sound than gases because in solids the speed being referred to the speed of longitudinal wave in the solid. This happens because they are much more difficult to compress. Solids are very difficult to compress than gases, and so they have higher values of B, that is bulk modulus. Solids and liquids have higher mass densities rho than gases, but the corresponding increase in both B, value of B of solid and liquid is much higher. This is the reason why the sound waves travel faster in solids and liquids. We can estimate the speed of sound in an ideal gas using Newton's formula and applying Laplace correction. Let us discuss. Newton's formula. For an ideal gas, the pressure P, volume V and temperature T in Kelvin are related by the equation PV is equal to N into Kb into T. Let it be equation 1. Here, capital N is the number of molecules in the volume V, Kb is the Boltzmann constant, and T is the temperature of the gas in Kelvin. Therefore, as assumed by Newton, for an isothermal change in the equation 1, we can write it as V into delta P plus P into delta V equal to 0, or rearranging this equation we get minus of delta P over delta V upon V equals P. Let it be equation 2a. Hence, we also know from our previous section that the bulk modulus B is given by the relation B is equal to delta P by delta V over V. Hence, comparing the equation for B in the previous slide and the equation of P 2a in equation 2a, we get B is equal to P. Let it be equation 2b. Therefore, the speed of longitudinal wave in an ideal gas can be written as V is equal to square root of B by rho. This also we have studied in the previous slide. So, the speed of longitudinal wave in an ideal gas, which was square root of B by rho, can also be written as V is equal to square root of capital P divided by rho, where rho is the mass density. Let it be equation 3. This relation is known as Newton's formula. Let us solve an example by applying Newton's formula. This is given in the insert box. Example: estimate the speed of sound in air at standard temperature pressure. The mass of 1 mole of air is given as 29.0 into 10 to the power of minus 3 kg. Answer: remembering that 1 mole of any gas occupies 22.4 liters at STP, the density of air at STP is given by the formula rho naught is equal to mass over volume, that is equal to mass is 29 given as 29.0 into 10 to the power of minus 3 and volume by definition is 22.4 into 10 to the power of minus 3 meter cube. This becomes 1.29 kg per meter cube. Now applying the Newton's formula given in equation number 3 as V is equal to square root of capital P divided by rho. We know the pressure at STP is 1.101 into 10 to the power of 5 newtons per meter square. Therefore, V becomes V is equal to square root of P is 1.01 into 10 to the power of 5 newtons per meter square divided by rho. Rho is 1.29 kg per meter cube, which is given. So the value of speed calculated is 280 meters per second. But if you compare this value from the value which is given in the table in the previous section for air, it is less by 15%. That is, the value in the table is given as 331 meters per second, whereas this is lesser than that. So there is some correction, there is some difference which was found by Laplace, and it is known as Laplace correction. Laplace correction, it was pointed out by Laplace that pressure variations are adiabatic and not isothermal. And who said? Laplace said that the pressure variations in the propagation of sound are so fast that there is very little time for the heat to flow to maintain constant temperature. Hence, the variations are adiabatic and not isothermal. So, he applied the correction. So, for adiabatic processes, the ideal gas satisfies the relation PV to the power of gamma is equal to constant. This also we have studied in section 12.8. Hence, delta of P into V to the power of gamma should be 0. Therefore, applying the knowledge of differential calculus, we get P into gamma into V into to the power of gamma minus 1 into delta V plus V to the power of gamma into delta P equals 0. Here gamma is given by the relation Cp by Cv, where Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. Thus, for an ideal gas, the adiabatic bulk modulus B adiabatic is given by equals B add is equal to delta P by delta V over upon V. That is equal to gamma V P, that is gamma P. Therefore, the speed of sound is therefore from the equations V is equal to square root of B by rho becomes V is equal to square root of gamma into P divided by rho. Let it be equation 4. The modification of Newton's formula is known as Laplace transform, the Laplace correction. So the equation 4 is the Laplace correction. For air, the value of gamma is 7 by 5. Thus, using the Laplace correction to estimate the speed of sound in air at STP, we get the value as 331.3 meters per second, which agrees with the measured speed. The principle of superposition of waves can be considered as the motion of two wave pulses traveling in opposite direction which cross each other. It turns out that wave pulses continue to retain their identities after they have crossed. However, during the time they overlap, the wave pattern is different from either of the two pulses, as we see during our discussion. If y1, y2 and y3 all of them are vectors or displacement at a particular time and at a particular position due to individual waves, then the resultant displacement is given by vector y is equal to y1 plus y2, vector y2 plus y3 plus etc. etc. This is the principle of superposition of waves. This equation, this wave function describing the disturbance in the medium can also be written as y is equal to sum of summation I equals 1 to n, that is sigma I equals 1 to n of fi x minus vt. Let it be equation 1. For simplicity, consider two harmonic traveling waves on a stretched string, both with the same angular velocity omega and wave number k, and therefore the same wavelength. Their wave speed will be identical. Let us further assume that their amplitudes are also equal and they are both traveling in the positive direction of x-axis. Thus, we can represent wave 1 as x of t is equal to a sine kx minus omega t. Let it be equation 2. Here, a is the amplitude, k is the wave number, x is the displacement, omega is the angular frequency. And second equation can also be written as y2 of x of t equals a sine kx minus omega t plus phi. Let it be equation 3. Here the two waves written in the equation 2 and 3 differ in their initial phase, that is phi. The resultant of this equation 2 and equation 3 is given by the superposition principle as y of xt is equal to equation 2 plus equation 3, that is a sine of kx minus omega t plus a sine of kx minus omega t plus phi. Let it be equation 4. This relationship of equation 4 can be simplified using familiar trigonometric identity for the formula sin A plus sin B using half angles. So simplifying, we can write equation 4 as in terms of half angles as y of xt is equal to 2a into cos of phi by 2 into sin of kx y minus omega t plus phi by 2. Here angle A can be written as kx minus omega t and angle B in the formula sin A plus B can be written as phi by 2. Let it be equation 5. This equation 5 is also a harmonic traveling wave in the positive direction of x-axis with the same frequency and wavelength. Please see, note, it travels, the resultant also travels with the same frequency and wavelength. However, its initial phase angle is phi by 2. So, initial phase angle is phi by 2. The significant thing is that the amplitude is a function of phase difference phi between the constituent of the two waves. So, the difference is the phase difference, that is phi by 2. So, we can consider three cases. Hence, the resultant is a harmonic traveling wave in positive direction of x-axis with the same frequency. However, its initial phase angle is phi by 2 but the amplitude is a function of phase difference. Here the amplitude is 2a cos phi by 2. Therefore, a of phi, a is the function of phi, that is phase constant, and is given by the relation a phi is equal to 2a into cos of phi by 2. Equation, let it be equation 6. Now, let us consider two cases. When phi in this equation is 0. So, when phi is 0, the waves are in phase. So, cos phi is cos 0. When phi is 0, the amplitude is given by the relation y of xt is equal to 2a into sine of kx minus omega t. Here, the amplitude is maximum and is given by the equation is 2a. A of phi is 2a. Let it be equation 7. In such a case, when the amplitude is maximum, it is called constructive interference. Please see the case. In the case of A, here two waves are there traveling superimposed with one another. So here phi is 0. In this equation, phi is 0 and the resultant is shown on the top figure on the right hand side. So the amplitude is 2a 2a and minus 2a, and the wave is traveling in the same direction with the same phase, but phase difference is phi is 0. This is 0. Phase difference is 0 here. In the next case, that is when the angle phase difference is pi, that is pi is 180 degrees. The waves are out of phase. Here cos phi, if you put the value of phi as pi, we get the amplitude y equals 0. Let it be question 8. Hence, please see the figure B. Here the phase is pi radians, and in such a case the one wave will travel like this blue line, and the second wave is a dotted line. When we sum up, the resultant is 0, and it is shown as a flat line on the x-axis. Important applications of superimposition principle are stationary waves and beats. These two topics, that is stationary waves and beats, we will study in next part. So this we conclude waves part 1. In the next session we will study about waves part 2. Till then, goodbye.